So welcome, Miss Anna, to Connected North at Home. Today we're going to talk about vacuum science, which is kind of a new topic for me, aside from using a vacuum to clean my house. I don't really know too much about it, but I know it's one of those concepts that we should be learning about just so we know how it works. So I'm going to turn it over to you and see you in, oops, I think you need to be pinned.
All
And
right.
to you.
Thank you. So today we are talking about the science of vacuums, but I'm not necessarily talking about that same kind of vacuum that we use to clean our houses. I do have something kind of similar. So I do have a oil-powered vacuum here. And so this is a really, really strong vacuum pump, which works similarly to the mechanism in your vacuum cleaner at home, where it creates suction, which can then pull dirt and debris off of things by moving air very, very quickly. But we're really talking about vacuums just like we're talking about vacuums when we think about outer space. So space is a vacuum. So if we're not talking about vacuum cleaners, does anyone have any idea what I mean by the vacuum of space? Let's see if anyone has any prior knowledge on the subject. If not, we'll talk about it all together, but I'd love to know what you think I mean by the vacuum of space. What does it mean? So once we leave Earth and we're outside our atmosphere, we enter the vacuum of space. Obviously, the vacuum of space, right, isn't a big machine. That wouldn't make a lot of sense. Kerrigan says black holes, gravity. So you guys are really thinking about some of these concepts that come into play once we leave Earth, right? There's certainly less gravity. And then on the opposite hand, black holes are actually have so much gravity that nothing can escape from them. So if anything gets too close to a black hole and gets involved in its gravitational field, everything gets sucked in. Gabby tells me that a vacuum sucks out all the oxygen. And Alec and Elise tell me that there is no air in outer space. And that is exactly what I mean by the vacuum of space, is that there is no air. Really, there's nothing until we get to another moon or another planet or another star. Everything in between those space objects, or in between our planets and stars and moons, is a vacuum. It's a void. It is completely empty. When I say completely empty, I mean totally empty. No solids, no liquids, no gases. That means no molecules or atoms, just like on my shirt, none of those whatsoever. And that's important for us to learn about because humans, right, are exploring space. We are trying to get to other planets. We send spacecraft all the way on to other star systems. We have telescopes that take pictures way out into deep space. So we need to engineer things that will go out into space and will be exposed to that vacuum. Now, we are very lucky because here on Earth, right, there's air all around us all the time. We need it to breathe, but we also need it for a few other reasons. There is an equal amount of air inside your body as outside your body. That means that we don't necessarily feel the air pressure all around us, even though it's there. There's about 14.7 pounds for every square inch of your body pushing on you of air. So think about a 15-pound bowling ball, right? That's really, really heavy, 15 pounds. It's a pretty big bowling ball, probably heavier than I would bowl with. But there's about one of those bowling balls pushing on every single inch of your body, which should be enough, right, to crush us. That's a lot of weight. That's much more than a human being could weigh. But like we said, there is an equal amount of air inside our body as outside our body. And so we don't feel it, and humans can exist really, really easily here on Earth. We survive just fine because we have adapted to this amount of air pressure. But if we go into outer space, right, there is no air, and therefore no air pressure whatsoever. And scientists and engineers really have to think about what's going to happen to these different objects or tools or devices that we send into outer space if we put them somewhere where there's no air pressure, right? Because we build things here on Earth where there is air pressure, and then we send them out of the atmosphere. And we always need to be sure that when we send something out of the atmosphere, that it's going to be safe, especially when it comes to things that carry humans, right? So we send humans into the vacuum of space on their way to the moon. We've sent them to the International Space Station, which is still technically in lower Earth orbit, so there's very minuscule amount of atmosphere there, but we want to send people onto Mars, and it takes about 6 months to get there. So scientists use things like this vacuum chamber, which is really just this plastic container hooked up to my vacuum pump, which can simulate the vacuum of space. So when I turn on the vacuum pump, there's a small hose that connects to the platform, and it's going to pull all of the air out of the container, all of the air, which will drop the air pressure down to nothing. And we can take a look at the different objects that we put inside the vacuum chamber and see what might happen to those different objects out in outer space. Does that all make sense? Tell me yes or no in the chat. Does that make sense what we're trying to find out here? So we've got some different objects. I've got some things that might do something surprising. I've got some other things that maybe are a little bit less surprising. Maybe we could really make some guesses about what's going to happen to all of my different objects inside the vacuum chamber. So let's get started. I think one of my favorite things to put in the vacuum chamber are these little marshmallow peeps. And so we said these are little marshmallow candies. So they're shaped like birds. They're just made out of a marshmallow, and then they're covered in sugar and dyed with food coloring. So the peeps will be the first thing that we put here inside our vacuum chamber. So we'll go ahead and we'll set that jar inside. We'll take a zoomed in look, and then we're going to place our vacuum chamber on, which creates that tight seal. And then when we turn on the vacuum chamber, what do you think is going to happen to the peeps? If you have a guess or a hypothesis, you can tell me in the chat. What do you think is going to happen to these marshmallow peeps? So remember that the vacuum is going to remove all the air from inside the chamber, all of the air. And then we're only left with those different objects inside. Guesses starting to come in. Maybe they could deflate, or they could squish together. They might float. They could look squishy. They could shrink or explode. So we've got some very different guesses here. So let's take a look. Go ahead and keep sending your guesses if you have them. And I'm just going to turn on the pump, and everyone watch carefully. Watch what happens. Wow, is that what we expected? A lot of people told us they might shrink. A few people told us that they could explode, but watch what happens, right? Marshmallows are full of millions of little microscopic pockets of air. So when we remove the air from outside the peeps, right, they have more space to grow. Those air molecules inside, they want to expand. They want to spread out and get as far away from each other as possible. And when we give them all this empty space around them, when we turn on the pump, right, those air molecules are able to do it. They're able to grow and fill the empty space around them. But let's try that for a little bit longer. Let's see. Now you'll notice that we get to a point, right, where they stop growing. And then pretty soon, we're going to see a point where the peeps actually start to shrink back down. That's because the longer we leave the pump on, right, the longer we leave it on, the more of those little tiny air pockets are actually ripping out of the peeps. So they're actually popping and exploding, and these peeps are losing the air that was originally inside them. So the peeps grew to a certain size until those air molecules started to reach the surface, and they started to be pulled out of the peeps, which made them not grow anymore. They actually started to shrink. But my favorite thing to do with the vacuum chamber, with all of our experiments, is going to be what happens when we let the air back in. So right now, this is still a vacuum. I could even lift up the chamber because there's so much suction, right, that was created when I removed the air, that I can lift the whole platform up just with this lid. So right now there's no air inside. But if I take off this hose, we're going to rapidly let all the air from the atmosphere rush in and fill that empty space that we created with the vacuum. So I'll zoom in because this is really, really fun. And let's watch what happens to the peeps. Now, if you said that the peeps might shrink or they might squish together, you were absolutely right. But that happened more when we let the air back in, right? We said that the longer the peeps were exposed to the vacuum, the more air we removed from the inside. So there wasn't as much air left over at the end. And so when we let the air back in, it was able to crush the peeps under the force of that 14.7 pounds per square inch. So now they're really, really small, kind of flat peeps, not as fluffy as they once were. Someone asked, can you still eat them when they're like this? And the answer is yes. I would say that if you like peeps, I don't love peeps, I really don't like the way they taste, they're a bit too sugary for me, but if you like peeps, you would probably like these peeps more than any peep you've ever had in your whole life because we've removed all the air from the marshmallow and now all we're left with is a really dense, sugary peep. So they're still soft, they're not hard, but all of the air has been removed from inside them. And so they're really, really flat. You can imagine like if you were to crush it into your hands, kind of like if you crush cotton candy down into a small little ball, right? You compact all that sugar and it becomes a really, really dense, sugary ball of cotton candy. That's the same thing we've done with these peeps, but we didn't have to use our hands. We actually just used the force of air pressure that's all around us right now. So that was pretty fun. So that was our first vacuum science experiment. Let's see, let's go ahead and try this one next. Now this is just a beaker full of water. I dyed it purple just to make it a little bit easier for us to see so it's not clear, but it's just water with some food coloring in it. So thinking about this same principle, right? Thinking about the same principle of this movement of molecules, what do you think might happen to the water when you put it in the vacuum chamber? When I turn on the vacuum and I remove all of the air molecules from the chamber, what do we think is going to happen to the water? Couple guess, maybe thinks it could make bubbles. All right. The water will bubble to get the air out. That's a great observation that there is still a small amount of air bubbles inside the water. It could become solid. Interesting. Yeah, it could become solid. It could turn into a gas. It might wobble around inside the container. These are fantastic guesses, everybody. Fantastic guesses. So let me share one slide with you really quick. Let's take a look at this diagram, which we've seen a couple times if you've been around for our other programs like frostology or some of our other Michigan Science Center programs. This is a diagram of our states of matter, right? And what it's really showing us is those atoms and molecules inside each of the different states, right? So this is a solid ice cube, and those molecules are really, really packed together. If we warm it up, right, then we can get that ice cube to melt into water, and those molecules start to move around and flow past each other. Even further, right, if we give it even more energy, we can cause it to boil, and those molecules will spread out and turn into a gas. But all these processes are reversible, right? We can also take a gas and condense it down into a liquid, which will pack those molecules a little closer together. And then we can turn liquids into solids, right? And those molecules just get even closer together and move even less. So let's go ahead and take a look at what happens to our beaker full of water when we put it in the vacuum chamber. So here we go. Wow, would you look at that? Our water is bubbling and boiling and turning into a gas. Now, this is clearly more molecules that were trapped inside the gas. This is really that water turning into a gas, turning from a liquid into a gas. So those molecules are changing their state of matter. They have more energy, right? They are really starting to boil. But let's take a look at something even more interesting. So I'm going to quickly turn off our pump, let the air back in, and then let's take a look at this. The water is not hot. Not hot at all. It's actually pretty cool. So I can touch it with my bare hands safely. So really, let's think about the science behind how this works. Normally we think of boiling, right, as putting a liquid on the stove and making it very, very hot, giving those molecules so much energy from the heat that they change state and turn into a gas, just like in our diagram. But we actually don't need any heat in order to do that. What we can do, right, is by taking away the molecules that were inside this chamber, right, we leave enough empty space, but what we've also done is we've taken away all of those really fast moving molecules from the container, which gives this, this can actually boil at much lower energy because it doesn't take as much energy to fill the air around it with the gas because the air around it is empty. It's a vacuum. So we can actually do this one more time. So I've got another beaker full of water, and this time I have a thermometer inside the glass. So let's take a look at the actual temperature change. I'm hoping you'll be able to see it when I zoom in. Hoping. If you can't read the thermometer, I know it's a little tricky. Let's see if I zoom in a little more, if we can see it a little better. All right, if you can't read it entirely, let me give you a reading from this thermometer, and then we'll take a look once it goes in. If I need to read it for you again, I can. So we're at about 20 degrees Celsius. You can kind of see it right there at the top. See where the red kind of meets the glass. Maybe if I tilt it, you'll be able to see it better. There we go. All right, so right now at room temperature, or where this water's been sitting at room temperature, we're at about 20 degrees Celsius inside the flask. Let's go ahead and we'll turn back on our vacuum chamber and a little, turn it so maybe we can see. Now let's watch that red line. Let's watch the temperature of the water as we start to boil it. Let's take a look. Here we go. The longer we leave this to boil, right, we should, in theory, or what we're normally used to seeing is that the temperature of the water would go up, right? Because we conventionally think of boiling as making water hot so that it turns into a gas. But can you see the line on our thermometer? Is it going up or down? Remember that it started at 20. Took it a moment to get going, right? So at first there was no change, but we had to give the water some time to start changing state. We really had to let the vacuum work. And now we definitely see a major change in our thermometer. The temperature is going down. That red line is falling. So now we're at about, let's see, we're at about 14. Instead of 20 degrees, we're at about 14 degrees Celsius. And it's getting a little bit splashy there inside our container. So let's go ahead and turn it off. Now we're at about 14 degrees, right? That doesn't make a lot of sense with how we normally think about boiling, right? Normally we think of increasing the temperature, but we've actually dropped the temperature about 6 degrees Celsius when we turned on the vacuum chamber. That's again, right, because we've actually removed all of the fastest moving molecules from inside. And really, temperature is just a result of kinetic energy, or the movement of atoms and molecules. You can think of this, right, if you were to take your hands and rub them together really, 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 really quickly, and the faster you rub them, the warmer your hands get. Heat is just a product of kinetic energy, even if we can't see it with our eyes. So heat is all around us because of the atoms and molecules in the air bumping into each other, causing friction, just like we see, or just like we get with our hands. Now think about the molecules that the vacuum chamber can remove. It's not here to remove solids or liquids. It can really only remove those gas molecules. And gas molecules are the fastest moving. They have the most energy. And so if we're removing those ones, right, we're taking energy from the system. Therefore, we are lowering the amount of kinetic energy inside the system, and the temperature starts to drop since there's less friction from those molecules kind of bumping around, causing that friction and causing the energy, or coming from the energy. So let's go ahead and we'll take that one out. And let's do another experiment here. I have another pretty fun one. This one, I want you to tell me, what do you think will happen to an egg inside the vacuum chamber? What do you think will happen to an egg? We can actually just try to put the egg right there. So tell me what you think. I'm going to wipe my container here so that we can see through it a little bit better since we've got some water drops on the inside. But tell me, what do you think is going to happen to the egg inside the vacuum chamber? All right, some great guesses starting to come in. Lots of people think that the egg might explode, right? That makes a lot of sense because if we take all the air from outside the egg, right, it's got nothing but empty space. Those molecules in the egg, right, in theory will want to expand and fill the space around it, just like we saw with the peeps. These are great guesses. Oh, and then May has a great question. So let's answer May's question before we do this experiment. The peeps had air inside them and they are edible. So what do astronauts eat and drink if they don't want the water to bubble? The simple answer is, right, the astronauts eat and drink inside the International Space Station, where we have pumped in air to make it livable. Astronauts can't live in outer space without a spacesuit. They don't actually eat inside their spacesuit because the hands are really big and bulky and you can't actually reach your mouth, right, because you're wearing a big old helmet that prevents you from being able to put something in your mouth. If you were to get a leak in your spacesuit, right, that would mean that your body is exposed to the vacuum of space as well. And if you know a lot about human anatomy, you might know that humans are made up of over 70% water. There's a lot of water in all of our cells and flowing through our veins. That'd be pretty bad, right? We saw what happened to water when it was exposed to the vacuum for just a short amount of time. In under a minute, right, though all the water inside this beaker started to boil. If astronauts were actually exposed to the vacuum of space without their space suit or without being inside a spaceship, all of the liquids inside their body would start to boil. It would be very, very dangerous. And if they don't get inside or fix the leak in their suit very quickly, they could die. So they don't actually eat when they're out in the vacuum. And so astronauts can really eat and drink. Things that people do here on Earth. They can actually bring real, regular food. They definitely still need to drink water in outer space, even more water than we probably do, because the air up there is so dry. They don't have humidity around them like we do to keep our cells happy and our skin healthy. So they still eat and drink regular food, but astronauts do eat what we call dehydrated food as well. So they'll actually vacuum pack or dehydrate, remove all the water out of certain kinds of food, like astronaut ice cream, which makes it really, really dry and kind of interesting and gross, but it makes it weigh less because water is very heavy. And so it takes less fuel for us to send that food up into outer space. And then they can actually rehydrate it by adding water once they get there, which is pretty interesting. So if you've never had astronaut ice cream, it's something that they sell at lots of different stores, or you could really easily order it online. I think it's kind of gross because it's got the texture of like almost chalk, but it tastes pretty good. So if you're interested in finding out what dehydrated food tastes like, there's also dehydrated fruits or things like that that you can get at the grocery store.
Well, the other thing, Anna, that we learned from our space session with Commander Pete was that the same little things that are in Lucky Charms they make them like ice cream, like astronaut ice cream. It's the same freeze-dried process.
That's exactly what astronaut ice cream is. They're just a bit larger. So you can get astronaut ice cream at the store, or if you can't find it, Lucky Charms do have the same thing. It's really just freeze-dried sugar and kind of fluff, almost like these marshmallows too. And so they take all of the moisture out of them and turn it into ice cream. It is not like ice cream. I think it's kind of gross, but
they're not free. And Lucky Charms are not free.
No, no, no. All right. Let's find out what happens to our eggs. We got lots of great guesses about what we think might happen to the egg. I love that we're basing it on the last experiments that we've done, using our prior knowledge that we've kind of gotten from here. But let's go ahead and let's turn on the vacuum. All right. Our egg has been inside for about 20 seconds now. Let's give it a little bit more time. We said it took under a minute for our water to start to boil inside the vacuum chamber, right? So let's give it maybe 20 more seconds, which will get us to a minute, and let's see if we see any results. Great observation. So we're not observing anything happening just yet, right? But by now, we have a total vacuum. We can tell, right? Because if I lift up my container, the suction has been complete. And so we have a complete vacuum inside the chamber, and really nothing happened to our egg, at least nothing that we can see from the outside, right? And this teaches us two important lessons: that some materials are strong enough to withstand the vacuum of space, right? So eggshells are incredibly strong, even though we might not think of them as being very strong because we are able to crack them open or crush them. They are incredibly strong. They're very, very structurally sound, which is important, right? Because they're protecting a living creature inside them. But right, there might be something happening inside the egg, but this teaches us a good lesson, right? That when we engineer things and send them into space, they're shaped, and the materials that we use are incredibly important. We want to use things like this eggshell, right? That when we send them into the vacuum of space, they're going to be safe. They're not going to grow to 10 times their size like the PEEP did. They're not going to boil when there's no air around them, right? So this egg would be an example of something that is a good material or a sound material for us to build spacecraft out of. But we can do something else with this egg, right? So Molly asked a great question about what was happening inside the egg. So we can take a look at that. So let's go ahead and I will crack the egg here. All right, so now we've got the egg out of its really, really strong shell. Let's go ahead and put it right there, back on our vacuum chamber. And let's take a look at what happens to the egg now that it's outside of its really, really strong shell. Let's see what happens. We've boiled our egg right here at room temperature, because remember, the egg didn't get hot. If anything, this egg got cold. So now the glass is much colder than when it started. So we did boil the egg. We saw all of those contents of the egg rapidly boil and almost rise up out of the glass, which we wouldn't want because it would make my vacuum chamber here a little bit gross. But we boiled the egg right here at room temperature. So we didn't cook it. This egg is still safe to eat, Charlotte, so I am probably still going to eat this egg. I won't throw it out, which is why I chose a glass for my kitchen instead of one of my beakers that I normally use for science. That way it's totally clean. There's nothing wrong with this egg. It might have a little bit less air in it than it did to start since we sucked all the air bubbles out of it, but that's okay. We could easily get more air inside of it right by whipping it very, very quickly or blending it up. So this egg is still safe to eat. It's not cooked. It is still raw, even though we boiled it, which is just kind of an interesting thing to think about. All right, we've got a couple more experiments to go. We have a different vacuum chamber here. So if I take my vacuum hose and I switch it over to this one right here, I want you to take a look at what I have inside the vacuum chamber. So inside this vacuum chamber, I really, really carefully hung something from the top of the glass. Now, this is a bell. So this bell is going to get hooked up to my battery here. So I've got a battery. Make sure I can get to my vacuum pump there. There we go. So I've got a battery here, which is going to supply electricity to this bell. And then there's a hammer. So right over here, this is what we call a hammer. Once we turn on the electricity, that hammer is going to swing back and forth. It's going to hit the bell many, many times per second. And then it's going to produce a sound. So let's take a look at that. So we could see that hammer start to vibrate very quickly, right? And sound is really just a vibration. It is really just the movement of atoms and molecules, because we say sound travels in a compression wave, meaning that sound energy will vibrate the air molecules from the source of the sound, which would be the bell, until it gets to the person who's hearing the sound, where it vibrates your eardrums, and your eardrums turn that vibration into sounds in your brain. So it's a not very complicated process, right? It's very, very simple. It just has to travel in a vibration. So when the battery is hooked up, we have vibration. When the battery is turned off, we have no more vibration, which means we have no more sound. All right, so let's go ahead and we're going to turn on the vacuum next. So I'm going to put this on here. We'll zoom back in so you can take a close look. And tell me in the chat, can everyone hear this sound? All right, great. So we can hear the sound. I'm going to keep it going. Let's go ahead and hook up our vacuum. All right. The vacuum is going on in 3, 2, 1. Can you still hear the bell ringing? No, we can't. But if you look carefully, right? If you look carefully, the bell is still ringing. Actually, we get this. I might need to back it up. So the bell never turned off. It was hooked up to the electricity the whole time. And let's do that again. We're going to do it again. But I want you to take a close look right at the hammer. So keep a close eye at the hammer. We could not hear the bell once the vacuum chamber was turned on, right? But take a close look at the hammer and tell me, what do you notice? All right, so the hammer is clearly moving. It's moving right now. Let's go ahead, and again, we're going to hook up our vacuum chamber and turn the vacuum on. What do you notice? As far as you can tell, is the hammer still vibrating? Is it still hitting the bell? Yeah, the bell is still ringing, technically, but we don't hear any sound. We can't hear the bell ringing because sound can't travel through a vacuum. We said that sound travels in a compression wave. Sound travels in a compression wave, meaning it needs atoms and molecules to travel through. So there's this saying that says, no one can hear you scream in space. And that's completely true. As scary as that sounds, you really can't hear anything in space because without air or without molecules, sound has no way of traveling from the thing making the sound to people's ears. So sound cannot travel through a vacuum because sound travels in compression waves, vibrating those atoms and molecules. With no atoms and molecules, there is no sound. But other things travel in waves too. So we said that sound travels in waves, and last week we learned that light travels in waves as well. So light travels in waves. So we don't hear sound in space, but do we see light in space? What do you think? They both travel in waves. We said we cannot hear sound in space. Can we still see light in space? It would make sense to say no, right? Because we said they both travel in waves. But you can see light in space. If we couldn't see light through space, right, there would be no sunlight here on Earth because the sunlight has to travel through the vacuum of space to get to us here on Earth. So light does travel through space because light doesn't travel in a compression wave. It doesn't need a medium to travel through. It can actually travel through a vacuum because it travels in what we call transverse waves. So those don't need a medium to travel through. It's just a frequency of light that travels in a wave to get from the source of the light to the person that's observing it or you're using it, because we said light isn't just visible light. We also have radio waves, we have microwaves, we've got UV waves, we've got infrared waves, right? So all of that type of waves, all of those kind of light waves can travel through space, which is how we can communicate with satellites using light waves. So we use infrared, or we use IR is infrared, but we use all sorts of light waves to communicate with our telescopes and our devices and satellites that are out in space because we can't use sound. So someone asked, let me look through the chat. Someone asked, they asked, how do they communicate? So astronauts usually inside their suit have two-way radios. And so they're able to communicate almost like walkie-talkies with each other, but they also develop some hand signals as well. So if they are out in space and they're both working on a project, they can communicate through their radio, but they can also use a variety of hand signals, right? Because we said we can still see in space, light still exists in space, but sound does not. And that also means, just like Charlotte says, that you can't hear spaceships and explosions in space. So if you've seen Star Wars or Transformers or another movie that has, fight scenes or explosions happening in outer space, they're really cool and exciting, but that is a little bit of movie magic, right? Special effects. We can't actually hear anything in space because there's no way for that sound to travel from the source of the explosion to the person who would be hearing it. So kind of movie magic, but everything, explosions aren't as fun if they don't come with a giant kaboom. So I can understand why they do that. All right, so I've got two more demonstrations to do. One more using our vacuum chamber here. This one is one of my favorites. Actually, I have two more. Always prepare a few extra just because I know how smart you all are. Always answer all my questions. So we have two more experiments that we can do. One of them using this little tea light candle. So I'm going to go ahead and I'm going to set the tea light candle right there on top of the beaker. Let's see if I can get my camera to focus. Not on me, but on the beaker. I'm going to light the candle. So someone had a great question, or Charlotte made a good point, right? That we can't actually hear explosions or anything like that in space. But I want to take a look at something kind of interesting. We're going to light this candle. Give it a moment just to really start burning there. Make sure that the candle is nice and going right. And fire, just like in this candle, is a combustion reaction, just like an explosion is. But we're going to go ahead and I'm going to let that candle start to burn, right? And we've talked about combustion in the past, that in order to have a combustion reaction, which is taking place right here, right, we need three things. We need three parts of the fire triangle. Does anyone remember those three parts of the fire triangle that we've learned maybe on Combustion or in one of our other episodes of from our Michigan Science Center sessions? Awesome, you guys, awesome. Heat, fuel, and oxygen, right? So we have all three of those things right here because we have heat, which came initially from the lighter, but is also being produced by the reaction. We've got fuel, which is the wax from the candle, and then there's oxygen all around us. But a couple of people already telling me what they think is going to happen when we put this candle inside the vacuum pump. So if you have a guess, what's going to happen to the candle when I put it here inside the vacuum chamber and we remove the air from inside? Go ahead and tell me in the chat, and then let's go ahead and take a look. Our candle is still burning right now because there's still air inside the chamber, but let's go ahead and take a look at what happens when we turn it on. Ooh, it tried for a second there. It tried to sustain itself. It really quickly, rapidly used up all that oxygen, and now there's no oxygen left inside the container. And if we're missing one of those pieces of our fire triangle, right, we can't have a combustion reaction. So the flame tried and tried and tried as hard as it could, but once there was no more oxygen left to be part of the reaction, the candle went out, right? So while we can have explosions in space, right, because normally those start from something that has some sort of oxygen inside it. So spaceships can explode in outer space. That's because they actually use liquid oxygen as fuel, which is highly, highly, highly flammable stuff. Especially when we're combining it with other things like liquid hydrogen, which acts as a great fuel. Liquid oxygen acts as a great oxidizer or accelerant, and then it just totally gets out of control very, very quickly because of how volatile those substances are. There can't be an explosion in space unless we were to provide some oxygen, right? Because that makes up our fire triangle. So really only things that we put into outer space can really ignite or be lit on fire unless it's coming from something like an asteroid, which might have some frozen liquid water on it, which contains both hydrogen and oxygen, right? So we don't necessarily have to worry about a lot of explosions in space unless it comes from something we built. But it's a really important thing to think about because, right, we're sending people into space, and so we need to make sure that we're always being safe. Molly said that this could be a fun way to blow out your birthday candles. If you have access to something like this vacuum platform, I highly recommend it. They are not easy to come by. It's something that we purchased from a scientific supply company. You just really need something that can form a really tight seal. You might be able to try to make one on your own, but again, it has to be completely airtight, right? It has to be something that you can completely seal so that when I remove the air with the pump, no additional air is able to kind of find its way into the chamber. So we bought this one because we also know that these materials like this plastic and the platform are able to withstand the vacuum, right? So these are strong materials. You can't make vacuum chambers out of just anything because if you make it out of something that's not very structurally sound, it could break. And so you don't necessarily want to do that, but it is a super, super fun type of scientific experiment that we can try all together. All right, one more experiment in the vacuum chamber, and then I have one other last kind of grand finale demonstration to show you. This is one of my favorite things, taking some shaving cream, which comes out of this aerosol can, right? So shaving cream is a liquid while it's here inside the container. But when you push it through the opening, when you squeeze the top, right, this is an aerosol can, meaning that it's going to fill that liquid inside with tiny little air bubbles or tiny little pockets of air, similar to our marshmallows. So let's go ahead and we'll just put some shaving cream right there inside our beaker. And so it looks like a kind of solid fluff, right? But we said that since it came from an aerosol can, we know that this shaving cream fluff is just full of millions and millions of tiny little air pockets. So tell me, what do you think is going to happen once I take the air out of the chamber using the vacuum? What do you think is going to happen to this pile of shaving cream? Ooh, great guesses starting to come in, especially talking about our states of matter. So Gabby tied it back to the peeps. It could do the same thing. Let's see, Addison thinks it could turn back to a liquid. That makes a lot of sense, right? Because since we're taking the air out of the chamber, right, we might return it to its original state that it existed in inside the can. It could explode. It could grow really, really big. Ooh, these are great guesses. So let's go ahead and let's find out what happens. Whoa, look at that. Our shaving cream is growing out of control. The expansion ratio of this stuff is crazy, right? It's much, much larger than our peeps ever got because it can really grow to almost an exponential amount of its original size. So the shaving cream has now completely filled the container. Those air bubbles inside have expanded. They've taken the foam with it, and they've really expanded to fill their container, which is one of those properties of gases, right? So we say that liquids will fill their container, but that liquids, the molecules still want to be near each other. They want to flow and stick together, even though they will fill their container. But gases, right? They don't want to be anywhere near each other, meaning that they will do whatever it takes to get away from each other. They will fill their container and try to keep going if they can. So they've filled all the empty space. But of course, our favorite thing to do is to let the air back in. So let's take a look. Oh, huge mess here inside my vacuum chamber. It is certainly not fluffy anymore. There's no fluffy shaving cream to be had. It's really turned back to a liquid, just like you told me it would. It smells really nice, which since shaving cream is kind of soap, it'll make it easy to clean later. But we do have one last experiment to show you, and this again ties to why we really study vacuum chambers, right? We said that vacuum chambers are really, really important scientific tools because it tells us about what materials will behave like in outer space. And we said one of the most important things we're trying to discover, right, is how do we keep our astronauts safe? I am going to have to do some cleanup today, which is why I always save that one for last, as you can tell. But I have a really fun experiment here, and I just need one other material. This is an experiment that you can try at home with some adult supervision because we're actually going to create a vacuum using temperature. And so what I've done before the program is I've been heating a can of water on a stove. So I have a tiny little hot plate, which is the same thing as a stove. So you obviously, if you're going to try this at home, are able to do the same thing. You can also heat up a can on the stove, but I've also put in a very, very small amount of water. So just a few drops of water into the can, and then I'm heating it on the stove. The other thing we need is some really, really cold water. And so I'm going to go grab that right now. Give me just a moment. All right. So I put some water in the freezer before the program. It's actually almost totally frozen on top. I'm just going to kind of break up that ice. It's not frozen all the way through, but on top we have some ice, which is actually fantastic because it means that this water is super, super cold. Now, we've talked a lot about how atoms and molecules come into play when we're talking about vacuums, right? When we heat things up, those molecules expand. They take up more and more and more space because that's what gases want to do. You can think of that just like what's happening inside this really, really hot can. So this can is now super hot, so hot that I'm not going to touch it with my bare hands. But it's so hot, and the molecules inside are really, really spread out. They have almost completely evaporated. The water has turned into a gas. But what I'm going to do is I'm going to rapidly cool them down by taking this can and submerging the opening, the top, into the water, which is going to cool down those molecules very, very quickly. And let's see what happens. Oh no, don't do this to me. Well, it's completely sucked up the water. So watch this. So if I pour it out, look how much water we've actually sucked up into the can. The can is almost completely full. And I have this problem occasionally when I do this demonstration. So I always have a backup plan in place. I also have a tea kettle. And so there's two ways to do this experiment. You can either take the can and you can put a few drops of water in it and then heat it on the stove until you start to see some steam rising up out of the can. Then all you need to do, right, is take a pair of tongs and flip it over, submerge it in that really, really cold ice water. But you can also do this using some boiling hot water. So I'm getting it boiled just one last time here. You might be able to hear that sound. So I have an electric kettle, and that's going to rapidly heat up my water, and I'm actually going to pour it into the can, and then I'll dump it out. So I'll give it just a moment here, and I see that a couple of people say that they drink bubbly too. This is my new favorite flavor. I just got it. So if you've not had bubbly, this is one of those things that's much better for you than soda because there's no sugar inside it. So if you can take it that there's no sugar inside bubbly, I think this one's super delicious. This one is the blueberry pomegranate. All right, since we're gonna work with some water here, I'm gonna grab a tray, just because I've been known to be a little bit messy. If you've watched Echo Live in the past, I like to make a big mess. It's one of my favorite things to do. All right. Our water is getting nice and hot. I can hear it starting to boil, but I'm going to wait until the light starts to switch off. But you can tell me, what do you think might happen if we get good results on this experiment? We saw at the beginning of it, right? We saw that this can sucked up some of the water, which works similarly to the vacuums in our house, right? When we heated up those molecules, they expanded, they took up more space. But what happens to those same molecules once we cool them back down? I'll leave in the chat. What happens to those molecules if we were to cool them back down very, very quickly? Think about what we've learned so far. If molecules spread out when they get warmer, what will they do when they get colder? As Emily says that the can would start to compress. That makes sense, right? Our molecules, if they expand when they get warm, they must contract when they get cold. So that leaves a big amount, a large amount of empty space inside the can, right? It really does turn it into a vacuum because all those molecules are going to contract, leaving a big empty space around them. And then what we should see is the effects of air pressure on this can when air is pushing on it from all sides. A couple of people saying that, thank you for understanding that. You know, it's sometimes I do mess up live. Not perfect, this is science, right? Sometimes there's these things called variables, things I didn't account for. Maybe I didn't let the water get hot enough. Maybe it didn't completely boil all the water inside, which might have given me some interesting results, but you're right that this is a great lesson that science doesn't work out all the time or every time. This is an experiment, but we're not going to give up. We are going to try it again because we can just easily set everything back up. That's an important lesson in all sciences that you should never give up. You should think about your variables, think about your experiment, and think what could you do differently to get you the results that you're looking for. Great point, everybody. All right, our water is still going to let it turn until the light switches. And so it tells me that it is completely boiling. That's as hot as it's going to get using my tea kettle over there. I can hear the bubbles starting to slow down, so I know it's getting there. Let's take a look. All right. Here it goes. So we've got our electric kettle. I'm just going to fill my can all the way to the top with this really, really hot water, right? So this water is boiling. It's just on the verge of turning from a liquid into a gas. All right, so we've filled it all the way to the top, all the way to the top. We're going to let it heat up the metal from the can for just a couple seconds here. I'm going to grab a glove. Gloves here. We're just going to go ahead, now that we've let the can really, really heat up, it's nice and hot. We're going to go ahead and pour out that water. Now, all we're leaving behind, right, is that really, really hot water vapor. And let's take a look. What happened to our can? Look at it now. You guys were totally right. The can was crushed or shrunk down under the force of air pressure, right? So this can is made out of aluminum. And when we left a vacuum inside the can, right, look what happened. Aluminum is not a very strong metal, although it's something we might want to consider when we send or build spacecraft, right? Because aluminum is very light, which means it would be a good thing to build spaceships out of because it won't cost us very much in fuel to lift this kind of metal off the ground. But would you want to be in a spaceship made out of aluminum? I don't know. Based on this experiment, I've got some questions, right? It's been crushed and it's got little holes in it where the metal has bent so bad, right? So maybe if we're going to build them out of aluminum, it needs to be a bit thicker because this material could not withstand the vacuum of space. It did not work very well at all. So I'm not going to outer space ever, probably, because I just don't know, but certainly not in a spaceship made out of bubbly cans. So that is all the experiments I have planned out today. If you have any questions, feel free to type them in the chat. I'd love to answer them if you have one. I know we've got a couple minutes left for questions if you've got them.
That was so cool.
This one, like I said, you can try it at home. So if you have a electric kettle, you can easily try this at home. You'll notice that I just filled the can all the way to the top, left it there for maybe 15 to 20 seconds so that we really heated up the can, and then dumped it out completely and quickly dropped it down inside our icy water. Again, you need to use either a pair of tongs or a glove because the can was really hot. It was full of boiling water, and you should definitely have some adult supervision if you're heating up the can on the stove instead.
Yeah. May would like to know, do you know any astronauts?
I do not know any astronauts. That would be super cool. We've had the Michigan Science Center has had a couple astronauts visit us over the years. I've never gotten to meet any of them myself, but there is an astronaut that's up on the International Space Station right now. He's from Maine. His name is Chris Cassidy, and he actually took with him a Michigan Science Center patch. So a patch that you would like iron on a jacket. He actually took one of those with him. Nice. When he gets back, he's going to give it back to us so that we can frame it and put it on display at the Science Center, which is super cool. So I don't know him, but he's doing us a really cool favor by doing that for us, which is just super cool. And we're so excited to have it back once it's here.
That's a real honor. Wow. Charlie and Charlie want to know, what is your favorite experiment you did today?
My favorite one we've done today is probably this bell in the jar, because I think that one's a little bit surprising, and I think it's an important thing to think about, right, is that we can't send sound waves through space. So I think that was pretty cool and unexpected. I really liked the bell, but you guys can tell me, what was your favorite experiment that you saw today?
I like the peeps. What was your favorite one, guys?
I like the peeps one too because I don't like peeps, and so it gives me a lot of joy once I see them all get crushed under the force of air.
Charlotte and Isaiah like the foam. Gabby said the foam or the peeps. Rael wasn't sure. I like them all. Katie, what did you like?
I liked the peeps too, because I'm not a big fan of peeps, and I really enjoyed watching them kind of get big and it's evil.
I'm making you a peeps cake in the summer. My peeps cake is really good.
Okay.
It's really gross. Would it work the same? Oh, Charlotte and Isaiah would like to know, would the shaving cream experiment work the same with whipped cream?
Yeah, it would, because they work on the same principle, right? So normally we think about our whipped cream, right? That if you want to use it, you have to push it through that aerosol lid. So inside is a liquid, but it's under pressure inside the can. So when you squeeze or kind of push on the nozzle, it works just like the shaving cream. It fills that liquid full of air. And so it would do the exact same thing.
Cool. And May wants to know, what is your favorite planet?
So my favorite planet is Saturn, just because I think it's the most fun to look at. It's got all the rings. And my favorite fun fact about Saturn is that the rings are only about as tall as the Empire State Building. And so even though we think of Saturn being really big, hundreds of times the size of the Earth, those rings, even though they're massive and very, very wide, if you think about how tall they are, they're only about as tall as the Empire State Building from New York City, which is crazy.
Awesome. So thank you. That was so much fun. I think the lesson next week is about
high voltage.
So electricity and high voltage. That'll be really awesome. We've learned so much from you. Thank you so much, Miss Anna.
Thank you, Anna. Yeah, that was awesome.
It was absolutely fantastic. We're so glad that we ended up having a big group, so we're thrilled. And we will see you next week. Have a great week.
Bye, everybody.
Bye, Anna.
Bye, everyone.